I should try to share my screen also, right? Yeah, I got it. So shall I just start? Can you hear me, Gaurav? Or anyone else?
Yeah.
Okay.
Okay. So it's a great pleasure to introduce Krishnan Rajkumar to the speaker today on telescoping continued fractions for several of long-region techniques. All yours.
Thanks, Gaurav. Um, I think I should apologize in advance. Generally, it has not been the best of times when I give a seminar, so please do not expect anything better. So sorry. But let me start. I think the beginning would be good. You may not be happy with the ending in advance. Okay. So view control L or something. You can see this, right? You can see this, Gaurav?
Yes. Yes. Yes.
Okay.
Well,
So thank you. Um, so I have a little bit of a longish introduction on the irrationality proof by Aperi. So the first statement that intrigued at least my research in this direction was this statement, this proof or this claim by Aperi, which says that zeta 3 is irrational. I do not have an expansion of zeta 3 in this paper. I'm sure I missed it. Zeta 3 is the sum of the reciprocal of the cubes, in case that was not known. And of course, the arithmetic nature of zeta 3, arithmetic nature of the even values of zeta, which is the sum of the reciprocal of the squares and the both powers, etc., was known to Euler. At least the expansion in terms of the formula in terms of pi, and later on, of course, the transcendence was proved. So all that was very well known, but Aperi's proof was a little bit of a first time that anyone really explored what it was about zeta of 3. So the intriguing part for me was the connection with Ramanujan. So I will just try to bring it up as quickly as possible. So what was Aperi's proof which caused a furore? It was like this. In 78, he made some claims. These claims look like this, that if you take this recurrence, it seems to have come out of nowhere. And you take the initial conditions again specified by him, they seem to satisfy the following properties. The solutions of this recurrence per se need not be, they're rational numbers. That's all we can guarantee in advance, though the initial conditions do look like integers. But first claim is they somehow seem to be related to zeta of 3. The ratio tends to zeta of 3. And here you go. This is the more surprising claim that actually whatever you do, the BIs are integers, integer values. All of them are integer valued. And AN has a denominator which is like this. This is the LCM of the numbers 1, 2, etc. up to n, which is literally the denominator of the sum of the reciprocal of the cubes. This dn cubed you see here, that is the denominator of the sum of the reciprocal of the cubes from 1 to n. And of course, you can ignore this fact for the time being, but the very fact that instead of having an n factorial cubed in the denominator, which is what this term would have implied, if you were just doing it, there were some miraculous cancellations which make the denominator very less in some sense. So anyway, and he also gave these numbers, what the actual solutions were, and caused some sort of furore. In modern times, once you know this formula, it's kind of easy to know that, see that there's a combinatorial, I mean, these are just combinatorial objects. These are the Aperi numbers, etc. And of course, the arithmetic nature that we saw here seems to be fine. And so is the ratio tending to zeta of 3. How to put it? That if you just look at this this expression in the middle, how do you hide this? Sorry, went back. This you can see what is on the screen, right? Yeah, the expression in brackets here, it tends to zeta of 3 as n tends to infinity. So this term kind of dominates. This n is in the denominator and goes rapidly to 0. So literally, this is the term that we are looking at as n tends to infinity. Uniformly, it goes to zeta of 3. So the ratio also goes to 0. So there's no big deal about this too, if you knew this formula. But then there was a big deal in knowing that they actually satisfy the recurrence. Now, these days it's done on a computer. Maybe those days the WZ method and all those were not invented in 78. So it was a bit of a bother, or maybe that even, I mean, nobody has written it down anywhere, but in my humble opinion, it seems like the discussion around this actually inspired creative telescoping and, all those other methods. Sorry, this is on record, but this is my opinion only. So anyway, this is the classical way in which the proof continues to prove that zeta 3 is irrational. Kind of irrelevant for us now. I can get back to it if there's time at the end. But literally, we try to get it, this sort of expression. Bn's and An's lead us to this what is called the linear form in zeta 3 and 1. So it's integer into zeta 3 minus another integer, which we have removed the denominator, etc. And that seems to go very rapidly to 0. It's a non-zero number. It's a non-zero real number, but as n tends to infinity, this goes to 0, and that concludes that it's irrational. It's a criteria, literally. So anyway, the main thing is that those constructions did appear miraculous and at that time, and then several authors after that came up with constructions of their own, involving integrals and polylogarithms and Pade approximations. The works, so many different options, approaches, all of them leading to the same sequences, yet there was some mystery about them, some miraculous nature, because they somehow don't seem to generalize to other constants. Maybe to zeta of 2, but not to zeta of 4 even, or 5 for that matter, is still unknown. It's still unknown that zeta 5 is irrational. So this was Aperi's construction. Aperi's proof, which came pretty much later, and it doesn't seem to be in a, I don't know, it's a paper which has no references. It's written in a very different style. Not very sure it's been peer reviewed, because there was a mistake. Math Senate review does mention that one of the claims is wrong, but that was not about zeta of 3. It was about log in that paper. Okay, so but this construction is what we are after today, and it seems to be related to Ramanujan. So what he does is he starts with this simple, the usual, it's finite series finite series truncation of the zeta 3 series, infinite series. Am I going too fast or am I overdoing it? Gaurav, I would like your opinion on this at least.
No, you're doing fine.
Thanks.
As slow as possible.
Okay, thanks. So you start with the usual finite series. So one is, so if you take the ratio P naught n by Q naught n, it's literally the finite series truncation. And then he starts by saying that, look, actually, they satisfy this recurrence. On the face of it, it looks somewhat good, but well, it's a trivial one. If you put 1, for example, it's just trivial. So starting from there, he goes on to construct more and more sequences by this method. So phi of n, I comma n is a polynomial in I and n. So, start from the previous row, it's almost like we think of P naught n and Q naught n as, let's say just P, for example. P naught n is the first row of a matrix. He wants to construct an infinite matrix with rows and columns going to infinity. So the first row is what we see here. And the second row comes from the first row by this method, and the second row gives third row, and so on. You can construct recursively all the entire matrix, or what he calls sweet doubles, sweet, yeah, two-dimensional array, if you like, two-dimensional array, yeah. So whatever it is, we construct two different two-dimensional arrays from the original series, and it's pretty straightforward. Now, there's really no surprises here. So this is many experts in the audience, I'm very sorry, expert in the audience would recognize this as the Bohr-Muir transformation, going from one continued fraction to another. So he didn't mention it. He didn't have any references, as you have just been told. Yeah, this is from there. So it's pretty easy to check that the new rows satisfy different recurrence. And this is again two-term recurrence, so it's continued fraction again. So that's what his title of his talk, his paper also was, interpolation of continued fraction. Then it's a no-brainer literally at this point, because the original sequence did go to zeta of 3, and you're coming up with some linear combinations of them only. So not only does the ratio goes to zeta 3, it's easy to prove. I have proved it in a paper of mine, but it's very easy. And also that the individual, say Q and you start with integers and you're taking linear combinations. They have to be integers, right? And similarly, this denominator. So these two facts are now trivial. And what's more, even the recurrence of the diagonals, okay, sorry, this should not have been here, but anyway, the diagonal sequences, you just take the diagonals, not along the row or along the column, but along the diagonals. And it's pretty straightforward to derive a recurrence that they will satisfy, because each row has a recurrence. If you go by it, even the columns have recurrence. We have this relation between three-term relation between different rows and so on. It's very easy to find out what recurrences satisfy, and voila, that's the Apéry recurrence that you had seen in the beginning. So there was no mystery here. I mean, that was the end of his proof. The mystery was, if you like, only the fact that you take, it's a polynomial here, and no, there's some more mystery, which we will, yeah, there's something more, that the convergence is pretty good when you go along the diagonals. That's the main thing, right, of his original paper. So that was Apéry's proof. He did not ever mention, and nowhere else in literature were we able to find it written down that there's Ramanujan. So okay, it'll come here. Sorry. So let me just complete this thread. So finally, what Apéry is able to prove is that zeta 3 can be written as is related to the following continued fraction. So what is P1 of I and P2? It's here. It's here. So this is the polynomial P1 of I, P2 of I, etc. And more specifically, this is what we are concluding from what he has said, that you take the specialization x is equal to I of this continued fraction written in Ramanujan's notebook. So this plus and minus, beg your pardon, it should have been this minus here. 1 by P naught x minus 1 power 6 by P1 of x minus 2 power 6 of P2 of x, and so on. So this is the continued fraction notation. In this particular equation is written wrongly, I would say. In later slides, finally, here it is. This is all the observation we have made. Of course, Apéry has done all his business. Somehow it was not published. So even there must have been some sort of resistance, or he didn't want to, or for whatever reason, it was not published in a prominent article, so it's even difficult to find any reference to Ramanujan. So the only reference to Ramanujan that we see is in Burnt, volume 2 only. After this entry, he does mention that this specialization x is equal to 1 plays a central role in Epery's proof. Of course, I asked him where it was written or how he realized it, but he can't recall. And of course, the son of Epery, in his biographical note on his dad, did mention that his constructions were motivated by a table of Ramanujan. So a number table, it was actually written number table actually. So no clue what really motivated him, but isn't it obvious now that, I mean, there's really nothing else that could have got his proof in this form unless he had actually seen this continued fraction of Ramanujan. Is my opinion again. So now, what is our goal in today's talk? I'll have to apologize in advance. I wanted to prove this by method of telescoping, but the slides have not been made. It will be coming up very soon on archive, but I hope I'll motivate you to, or I'll intrigue you a little bit so that you might actually read it when it comes out. Okay, so what is the method that we have in mind? This work by Gaurav and me, Gaurav Bhatnagar and myself, which we published a couple of years back. And we were looking to prove low bounds for the error term in Stirling's approximation. So by Rn, we mean this extra term that's unaccounted for by Stirling's approximation, which is the main term. So we call it error term, or it's also called the Binet function, Binet, right? B-I-N-E-T function in literature. So what was our goal? Our goal was to get lower bounds. There were many articles in literature, not mentioning any of them here, where several lower bounds have been derived, including a work by so, Robbins. But yeah, the main work by Robbins, where he derived a lower bound for Rn in just a little small terms. But anyway, we are trying to find the lower bound in a more generic fashion. We were trying where the lower bound is almost like a continued fraction with appropriate numbers for the AIs. Okay, so and how did we do it? So, I mean, we did it also. For example, we were able to prove that if we make this choice, it works for all n greater than or equal to 1. That was our goal. Literally, in the classical approach, by using the Stirling series, which is coming from the Euler-Maclaurin summation formula. So there's this asymptotic series involving the Bernoulli numbers. So of course, asymptotic series do have lower bounds and upper bounds of their own. So it's not difficult to derive those upper bounds which hold for large enough n. Any given upper bound will hold for large enough n, but we wanted bounds which will hold for all n, which is useful in computation. Large enough can mean tending to infinity, right? So in most cases, those bounds were not guaranteed. That's why many authors had worked on this. And for example, we were able to derive this, which kind of beats all the lower bounds known till date. And of course, the method was powerful enough, which I'll just briefly explain here, that we can actually derive, I mean, conjecturally, we can go lower bounds of any order, actually. And there was a conjecture also there. Unfortunately, we couldn't complete it at that point of time. The method is to first, so this is just, getting back to the zeta 3, the continued fraction that we saw in Ramanujan's notebook. There was a series, there was an infinite series. It's almost like the tail of a series. So similarly, here we also had an expression. Everyone knows this simple expression. It comes from the classical methods that Rn is actually the tail of an infinite series where this, which is expressed in terms of log. So if you take the log of the whole thing, you get into some very simple expression of this sort. The infinite sum is just coming because of this, this constant square root 2 pi, which actually comes from the whole sum. So the tail is related to one of these constants. Okay, so finally this is what we have. We have an infinite sum of logs. So what were we going to do? We were going to actually take this very standard continued fraction for log p plus 1 by p, and it is very closely related to the Legendre polynomials, the numerator polynomials as well as the denominators is more classical Legendre polynomials. So somehow, whatever the approximations are, you go to the nth convergent of this, it will be related to the some nth Legendre polynomial, some version of, some transformation of. Okay. And then what would we about to do? We do get, and this is, this negative, the minus signs indicate that this convergence, increase to epsilon p. Epsilon p is here. So convergence with appropriate multiplication of 2p plus 1 by 2 and minus 1, we will get an increasing sequence of convergence going to epsilon p. So there we get it. For each such convergence, okay, went down. Oops, sorry. Okay, for each such convergent, we find A1, A2, AK such that if, sorry, epsilon p is greater than gk of p minus gk of p plus 1. So basically, not only do we have a rational function here as an approximation to epsilon p, that rational function itself has a lower bound, which is some sort of difference, gkp minus gk of p plus 1. And where does the word telescoping come? Because when you add up all the lower bounds, gkp minus gkp plus 1 and so on, when you add them all up, it telescopes, and you're left with only gk of n as a lower bound for Rn. So literally, if you're able to get a lower bound of this in terms of a difference of continued fractions, then your original term Rn has a lower bound with that very same continued fraction. So that was the idea, and there was an algorithm, and there were a lot of conjectures, etc. That was a longish work. We will have occasion to talk about it some other day. What was I planning to do in this work? Planning. It's going to be a letdown. I'm going to apologize in advance. Or I can, if I have enough time, Gaurav, I can probably even write on and explain what I had. Sorry, sir. First, let me complete what I have written. So this is one of those continued fractions that actually we were referring to in the abstract. So these are all entries from Ramanujan's notebook, volume 2. Corollary to entry 29 is this. Now, what is the significance of this continued fraction? Of course, it's an infinite series. It's written in a sort of, we can already see some telescoping. So what are we wanting to do? So basically, this is a series. If you put, for example, x is 2. X is 2, it's 2 times minus 1 by 3 plus 1 by 5 minus 1 by 7 and so on. So it's related to the alternating sum of the reciprocals of the odd numbers. 1 minus 1 by 3 plus 1 by 5 minus 1 by 7 is the famous Gregory-Madhava series of pi by 4. So this is related to the error term, or what do you say, the tail of that series, for pi by 4. Now, what are we trying to do here? Okay, there are more entries which I'll show you first only. So this other entry, which already, I mean, as soon as you see it, now I hope the patterns are already coming in your mind. So I was just trying to intrigue you in this talk here. Zeta T2 is pi squared by 6. And there is an entry which is related to that, I claim. Basically, if you write in x place, you write 2x minus 1, there will be a sum of the 2 coming out as well. We are half of x plus k whole squared. That's what we would like. If you replace x by 2n, for example, then whatever this 1 by 4, 2 by 4, so that is half times summation k equal to 0 to infinity, 1 by n plus k whole squared. So that is literally the tail of the series for zeta of 2, which is the reciprocal of the squares. And that's how it's related to pi squared by 6. On the right-hand side, of course, we see continued fractions of similar sorts, and we are wanting to have telescoping continued fractions for prove these by the method of telescoping continued fraction. We want to prove this equality, and each term we will actually replace by difference of continued fraction. That is the goal of the talk. So this is the zeta 3 which you have already seen, and this is exactly what we had when Bruce Byrne was talking about, and we saw it in Epery's proof also. So this is literally that continued fraction. So I claim that it can be proved by the method of telescoping continued fractions. And the final one is here. This is related to G. I have written G. For example, x is equal to 0, 2. X is equal to 2, if you like. 0 is always tricky, you see. So, but anyway, if you just had 0 for the sake of argument, if you just had 0, it's the alternating sum of the reciprocal of the squares of the odd numbers. 1 by 3 squared, no, I mean 1 by 1 squared minus 1 by 3 squared plus 1 by 5 squared and so on. So that is the constant called G, Catalan's constant it's called. Nothing is known about its irrationality as of today, but at least the continued fraction is straight from Ramanjan's notebook. There we go. And I again claim that this can be proved by the method of telescoping continued fraction. So what is the goal of my paper? My talk was to just tell you that we can use this method to actually prove these continued fractions for generic values. So what Epery had done, for example, he had only proved it for specializations, x is equal to I. He had proved this one. He had proved it for specializations, x is equal to I. But by the method of telescoping continued fractions, we can actually do it for a huge range of values. Maybe not the full range that Ramanjan claims in the notebook, which was real x greater than half. That may or may not happen, but at least real x greater than 1 for sure will happen. So I'll just show you. This is all the slides I have. So first I'll show you the slides. So this is what we're trying to do is to prove this continued fraction. Okay, so this 2 has been you just let's just go with this with the flow for time being. I'll just write it down and explain it to you in a better way. And probably related to the method of telescoping. So the first correction term is just by first correction term, we just mean, continued fraction, the first convergent of the continued fraction. Or in the method of telescoping continued fractions from Gaurav and my paper, when k equal to 1. We're going at k equal to 1, k equal to 2, and so on. We're trying to find better and better approximations to the individual terms. Okay, there we go. Okay, so this is what we want to do. I mean, we're claiming that this is a good approximation. So right now we're not discovering anything. We're just, Ramanujan has given it to us on a platter and we're just going to prove it. That's the goal for now. We have 1 by 4x. Why is this 4x? There was a 2x earlier. X has been replaced by 2x. K goes from 0 to, okay, when k equal to 1, you have 2x plus 1 as the first term, and we're trying to approximate that only. X has been replaced by 2x, and there's a 2 factor which has come here. That's the 4x that you can see there. So this is what we are saying. And why is this true? I mean, this is obvious, like, I just wrote it down to say that, look, if we just multiply it by another 2x plus 8x plus 4, okay, that's my down here. I hope you will silently leave. Multiplying by 8x plus 4 both sides just gives you this. And it's pretty clear that, there's a less than here. But actually, when you take the difference, it's like 4 by the difference between these side, left-hand side and right-hand side. It's a 4. The 4 that comes here is a 4 by the product of these big polynomials. So it's a smallish difference. As x goes to infinity, it's definitely, but we're not taking x to infinity. X is a finite number. So it's a small number, the difference. So anyway, this is just a telescoping. I just wrote it down. I'm so sorry. I did it, but this is what I'm trying to say. You start with 2n plus 2k plus 1, right? When k is 0, you have this. When k is 1, you have increased n by 1. And then, 2 and so on. So there's a nice cancellation and all you're left with is the first term. So literally you got an upper bound as 1 by 4n. And what about the next term? Next term is, let's just go to the next term. So what is this expression I have written here? I've just written the second convergent from this with the 2 absorbed in. So please bear with me. But finally, there's an x by 4x squared plus 1. That's the second term, x by 4x squared 1 plus. And there's a the most important thing is that telescoping is what we had done in Gaurav's with the paper with Gaurav was we had written epsilon p is approximated or lower bounded by gk of p minus gk p plus 1, because the overall the series was a simple sum, whereas in this particular case it's an alternating series. This one is an alternating series. So we have written gkp plus 1, and so that eventually telescopes. So that's what, hopefully I have conveyed that in this. There's a plus here, there's a plus here also. The plus here, and then there's a minus in the next one, and so on. That's what we wanted to do. That's why there's this plus here. And how does this work out? So overall, it works out pretty fine. Again, there's a difference of 4 only in the denominator. If you just cross multiply and all, that's the difference. So eventually, the first term that you get here is a good enough approximation. It's actually a lower bound also. So we come up with series of upper and lower bounds. There's no conjectural problem here because all of these series are polynomials with positive coefficients, and the difference is also stuff we have a very good handle on. So the convergence, to prove convergence is pretty straightforward. Before I have some time left, no, Gaurav? This is all I have in this slides. Sorry. This is all I have in these slides. How much time do we have left, Gaurav?
You can take another 20 minutes if you want.
20 minutes.
Or something.
I'll just write down the equations, which I apologize I could not do on the in the slides. I'll just use I'll stop share once. I'll share this other screen. I should probably just show you Ramanujan notebooks once, just, if I have missed out something. I mean, if I missed out the entire screen, why not? Okay, first let me just show you Ramanujan's notebook. So here it is. So this is one of those corollaries, which is related to G, the Catalan's constant. So yeah, instead of going around the continued fractions for these constants, the idea is, so if one has to go towards irrationality proofs, of course it has been shown again here, as we have seen. This is Bruce Burn's writing actually, that the same infinite set of continued fractions was found by Henry Cohen, who obtained them from a different formula. So Henry Cohen and Georges Rhine uh, did a lot of work on this, but for some strange reason, pretty unfortunate for all of us, they haven't published anything. And not only that, they had given a series of talks on this to several experts. So most experts do feel that this has all been done before, and still it's not published. Anyway, that is the unfortunate part. But Henry Cohen has very kindly shared his slides of the talks which he has given in late 70s, early 80s with me. So it's probably available for anyone who's just asks. This is one thing. This is so the irrationality proofs would come by varying the values of x successively, and hopefully we will get irrationality proofs. Of course, they didn't get it. That's why they probably didn't publish it. So this method probably does not yet yield a irrationality proof. So here is another continued fraction which I haven't shown in the slides. So this is another continued fraction for yet another continued fraction for the same pi by 4 constant, except it's in a different form here. There's a 2x factor. So there's a lot of hope from my side that this yields yet another proof for pi by 4, irrationality of pi. There's a hope. But as of now, the irrationality proofs for zeta of 2, so this is a zeta 2, 1. Irrationality proofs for zeta of 2 and zeta of 3 have already been derived by Aperi in his paper. And yeah, his method is the one that stands right now. And yeah, there's just too many of them. So this is the Ramanujan's notebook. Let me just, any questions before I write something so that I can write something more specific in answer to your question? Okay. So what is the real method that we have for proof? So the telescoping continued fraction. So I'll just start with, for example, the one which I was describing. This one. So what we want to do is we are looking at this continued fraction minus 1 to the k. We are having here 2x plus 2k minus 1, isn't it? Yes. And k equal to 1 to infinity. So this was how it was. I'm just making sure the numbers are not wrong. K plus 1. Yeah, this is wrong. It was wrong, whatever I will do. So we should just start from That was k plus 1. And there was a 2 here, and this was 1 by x squared by, was it x? No, this was when it was x, so we have to put a 2x here. Fine. So this is the unknown fraction we are out to prove. So literally what we want to get is to start with the first term, which is 2x plus 1. We want it as a, let's say we'll just put it here for time being, approximation of Pn by Qn plus Pn. So this is x here. And we had invented this nice notation in our paper. So let me just use that. Qn plus. So what do we mean by Pn plus? Pn is actually Pn of x, and Pn plus is Pn of x plus 1. So we're just increasing by, and same for Qn. So we are just having same rational function with x replaced by x plus 1. And there's a plus term here because it's an alternating series. Okay, so this is what we want to do. So what we literally want to do is to find the difference between this, which is what I was trying to point out. So the difference, let's say dn, is the difference between these two as a rational function. So you have 2qn plus minus 2x plus 1 into qn plus. This is the difference. So basically, when you take the difference between them, the 1 by 2 x plus 1 minus RHS would actually be dn by, of course, you have 2x plus 1 to whatever it is, qn plus. So the difference between this term, your individual term of the series, and the approximation would be of this form. We would really like to know what is dn. Of course, just going, I'll just explain the method in a bit, but we are able to prove that dn is, let me just complete that to show that this actually, the continued fraction converges. To cut the long story short, dn is minus 1 to the n two times n factorial squared. N factorial squared. So it grows like n factorial squared. It does. But it's a constant, it has no dependence on x. All the x terms like get cancelled, like we had seen in these two terms, explicit terms. And how do we prove convergence? That's I don't know. This is just it's just, again, this is all undergraduate type maths. So if the claim will be that, so Qn, we have this Qn is here. What is Qn? Oh, we don't have Qn. Okay, let's just write down the recurrence for Qn. Qn plus 1 is n squared Qn minus 1 2x Qn. This is the recurrence. And we want to prove this. We make this claim that Qn is bigger than n factorial times some power of n. I'll just call it alpha for time being. It's where alpha will be, let's say, some number less than half. And we will choose. We will choose a number which is slightly less than half. And we'll prove this by induction, basically. So how do we prove that? So if that is true, for example, if this is true, this is the claim I wanted to write. Claim. If this is true, if Qn grows like n factorial in power alpha, then you can see that this difference, the numerator is like n factorial squared and the denominator is like n factorial squared n to the 2 alpha. Yeah, so that goes to 0 as n tends to infinity. That's all for a fixed x. For a fixed x n tending to infinity, we will have this convergence. So this will, converge as n tends to infinity. So finally, what do we get? So this is the telescopic continued fraction that we were saying. So when you have the alternating sum of the series, these continued fractions will telescope and you will be left with the first term. And this claim is like, again, sort of it would be trivially done. There will be a small dependence of alpha on x. Other than that, this sort of condition will come up. Rather than pushing the details on you, this is the basic idea of the proof. Again, if you have any questions, I would be glad to answer. What appears to be surprising is this the correction term that I was referring to, the word. This actually, the word comes from a talk on ancient Indian maths. So there's this person called Madhava who lived in 1400s and discovered this series, for example. He even gave correction terms for the error term, for the finite truncation of the pi by 4 thing. So literally, he gives a correction term for our continued fraction only. And those happen to be, for some strange reason, he gives three correction terms, all three of which are actually the first three convergence of this same continued fraction of Ramanujan. And what is even more surprising is in a paper written in, again, history of maths only, it appears that this same telescoping method is literally what the person who has written that paper has used. I'm not sure if that was in Madhava's mind or not. How will we know? Unless we read, or it's probably not written in. That was that historical bit. That the word correction term comes from Madhava. Okay, so actually that's all I have. More I will write in my article. It will come up very soon. I'm even hopeful that it can to extend to new irrationality proofs, but that's not sure. I have not done the calculation to confirm that. But all these continued fractions that I showed here, all of these, the difference, the dn terms that I was calculating, again, we get constants. That's the miraculous part. For each of these, for the zeta 3, of course, Aperi himself, his proof hides that. So that was the miracle in his case, he says in his paper also. So the miracle is that the difference is n factorial power 6. Difference between this one and the finite truncation, the numerator of that. The denominator is a product of so the but each of these other things also, the G also, each of these have the same property. That's the discovery.
Just to understand,
Yeah,
sorry, I missed out some part because my internet died
I
and
see.
I came back. But you're taking the first term and then writing it as the difference or sum of continued fractions. Then you take two terms and see what is the sum, and then three terms and so
Yeah,
on. And then
just
method
for
of
this continued
undetermined.
fraction given here, it works out perfectly as you have said.
And you discovered all these one square and two square.
Discovered as in, I don't have a way to
I
come
mean,
up
they
with
come out
these.
in the calculation.
They don't come out. No, if I put it into the recurrences, I get the difference to be tame and well behaved.
No.
I mean, the other way around. I can prove these continuous fractions. I have no clue how it can be discovered on a, unless, of course, there's the algorithm given in the paper with you. Maybe we should run it through the algo and then, prove that this comes out. That is not yet done.
So the A1, A2, A3, like you were doing last time, this not calculated this.
We didn't calculate it. I just gave this into the algo and it worked out.
Oh.
I mean, this is a very milder version of what we were doing in that paper. Except the convergence is very natural because all the series involved are positive coefficients. And as I've just shown you, the numerator by denominator goes to 0. That can also can be proved. So convergence is a given in this. How to discover them is something I have in thought of. Yeah.
On Ramanujan, we don't know how he proved.
No clue at all. But it seems now I have already shown you. Were you there when I showed you? There are more continued fractions actually. Here it is. Why should I hide it from you? It's Ramanjan's notebook. Here it is. So there are more continued fractions which I didn't show you. 32, 2, 32, 1. For example, there's another one. It's slightly different because there's a 2x involved here. It's not a proper sum of series fx plus 1, etc. Yet still it can be proved. I have a vague proof of it. And there's another one for G. Again, 2x squared in this case. No clue what Ramanujan had in mind, actually. So in Berne's proof, actually, most of Berne's proof relies on, like, for example, in zeta 3 proof, he starts with entry 35. So entry 35 is that crowning glory of the product of gamma functions of Ramanujan. So from there, he derives all of these. But it's difficult to believe that Ramanujan first derived the gamma one and, derived all these as corollaries of that. Yeah, he must have had a method leading up to that, right?
Well, yeah, so, of course, I don't know. I mean, who knows? But one approach that I found for a lot of the Q continued fractions was a way to just divide two series over series. And in that you could sort of predict. You start with some two series which have some sums, and then you expand the series, and then you get in the Q form. But I haven't checked these. These are still pending for myself because one of current
I think
students
it's simpler
has
to
a
have a, I don't know. Once we see
yeah,
it, it
yeah.
seems pretty natural, actually. Who knows?
Well, in Q continued fractions, all of them work like that. So
Mhm.
so the conjecture is that that technique, and that technique was known to Euler and Gauss. So
Mhm.
Alan Sokal has written a big paper on that algorithm. So he calls it Gauss's algorithm. But it's been around, so it's not difficult to believe that Ramanujan didn't have it. He probably used it too. So yeah, I mean, he discovered a lot of stuff which he studied.
This seems different. And besides, see,
This
again,
is
stuff
different.
which we have missed out is these other ones. This is what Aperi had used because it's a neat form. But the original one is, more of that scale J's type.
Right.
Yeah. And who knows, for higher zeta values, nothing has been written. It's worth pursuing, actually. Just to see what continued fractions come. We don't need to get irrationality proofs or anything. Of course, for zeta of 4, there is a continued fraction by Cohen in his paper. I think I could share it with you either, but I'm sure he would share it with you if you ask. It is not, it doesn't have a neat form like this, whatever he has derived. Yeah. It's not it's a series of continued fractals, different ones. It's not related to one unified element. That's the problem.
Krishna, may I ask you a question?
Yes, please.
Yeah. So, I mean, all of these continued fractions of Ramanujan are very beautiful, and I have trouble understanding them because I'm trying to translate them in my own mind into my own way of thinking about them, which maybe you can help with. I mean, to start with, if I understand correctly, all of these continued fractions should be understood analytically. That is to say, there is some region in the complex plane where the series on the left-hand side converges, and the continued fraction on the right-hand side converges, and they're equal, right? Is that right?
Exactly,
okay.
That's right.
Okay, so I like to think about continued fractions as formal power series in some indeterminate.
Okay.
So I guess the indeterminate here would be 1 over x or something like that. And then the second thing is I prefer to have my continued fractions where the indeterminate is in the numerator, not in the denominator. So for example, Stieltjes would write continued fractions as 1 over z minus blah, blah, blah over z, whereas I prefer to write a Stieltjes continued fraction as 1 over 1 minus alpha 1 t over 1 minus alpha 2 t, and so on. Right? So I'm trying, so I want to try to make these two translations of all of these things. And so to rewrite each one of these continued fractions, for example, well, maybe the one you have, entry 32.3, is not the one I should look at because the denominators are not just x. But if you take one of the simpler ones, take one of the simpler ones, like that, like any of these. So I would like to rewrite this. So I would like to say 1 over x is t, and then I would like to reorganize it so that the t's are in the numerator rather than the denominator, and see what this says.
Sure, that should be doable.
Yeah, I mean, so it's just a translation, but I think
how does it help you in the sense you have combinatorial interpretations for them?
Well, maybe. I mean, as I say, I like to think of. Combinatorialists like to think of power series in positive power of something, and so what combinatorialists call a Stieltjes type continued fraction is not the way Stieltjes wrote it. It's a power series 1 over 1 minus something times t over 1 minus something times t, and so on. And so I would like to rewrite these things in that form, because then maybe, well, I don't know, then maybe some of the things that we do on these power series would become easier. Well, easier for me to understand. So it's just a question of translation, but it would be interesting to see what the translations look like.
Sure, I'll try to do something and write to you.
Yeah, maybe starting with the simplest ones here.
Yeah, sure.
Thank you.
Thank you.
If you take x out, then you'll get 1 over x squared and then 1 over x cubed and so on.
It does. Yeah, I don't even want. 1 over.
I'm not.
So if you just take x out, so you'll get 1 plus 1 over x squared instead of x. Then you take x squared out, then you'll get 1 over x cubed and so on. So it will become t squared t cubed. So on.
Is that true? Is that what you get? No, it can't be.
We'll have to think it out. Think it over.
No, it can't.
You can think about it.
You're factoring it out.
No, it can't be that. It can't be that.
You're factoring it out, right? You're factoring out the x from the bottom. So just take x common from the second guy. So it's x plus 1 square over x, right? So if you take x common, you'll get 1 plus 1 over x square, then you take x square common and you get. So just do it an infinite number of times. And then
No, it can't be that the powers. It can't be that the powers go up and up and up, because if that were the case, then you would with, I don't know, with n convergence get something accurate to order n squared. That can't be right.
I think we'll write it down and send it
Yeah,
across.
I think one just has to sit down and work out what it translates to.
Yeah, sure. Yeah.
But then one has to also see what happens to the coefficients. I mean, when written this way, the coefficients are nice integers. I think it will turn into the coefficients being rational numbers, but okay, that's fine.
So we'll try.
Any other comments or questions? Okay, then let's thank the speaker.